Good morning and welcome to Advent of Code in F# day 11. Yesterday was a bit of a tricky puzzle for me because I dislike mutable data structures. So I hope today will go a bit faster. Let's see. Seating system, alright. Our plane lands with plenty of time to spare. The final leg of your journey is a ferry that goes directly to the tropical island where you can finally start your vacation. Whew, after 11 days of travel. As we reach the waiting area to board the ferry, we realize we're so early nobody else has arrived yet. We're going to model the process people use to choose or abandon their seat in the waiting area. Pretty sure we can predict the best place to sit. Yeah. Algorithms to predict the best place to sit. A true programmer. So we get a map of the seat layout, which is our input. And here we go, two-dimensional grids. Again, each position is either floor, represented by a dot, or an empty seat represented by an L. Okay, that kind of looks like an empty seat, sure. Occupied seat is a bang. Okay, no. Let's call this a pound. For example, the initial seat layout might look like this. So floor, empty seats, and when people sit, it's a pound symbol. Now you just need to model the people who will be arriving shortly. Fortunately, people are entirely predictable. Yeah, sure. And always follow a simple set of rules. All decisions are based on the number of occupied seats adjacent to a given seat. Hello. Game of Life. Yeah, this sounds an awful lot like Conway's Game of Life. Yeah, so you look at the surrounding seats, one of the 8 positions immediately up, down, left, or diagonal. Yeah, following rules are applied. If a seat is empty and there are no occupied seats, it becomes occupied. 4 or more, the seat becomes empty. I'm going to look up Game of Life. Is this literally Game of Life? Don't remember the exact rules. Fewer than 2, 2 or 3 lives, more than 3 dies. So no, it's a variation of Game of Life, but it's very similar. Okay, so we have rules. The following rules are applied, and they are applied simultaneously. So every rule applies in the same instant. Cool. Floor never changes. Seats don't move. Ah, that's also interesting. So we don't only have like empty spaces, but we have floor that nothing happens to, and then we have seats. Nobody sits on the floor. Cool. After one round of these rules, every seat in the example becomes occupied because if a seat is empty and there are no occupied seats adjacent to it, yeah, makes sense. After a second round, the seats with 4 or more become empty. Yeah, it's too crowded for people, they leave. Cool. And this keeps on going until the chaos stabilizes. Okay, so we need to find a fixed point, or we need to find the moment in time where no changes happen. And then we count the number of occupied seats. Okay, that's clear. Let's grab... Oh, this is a big map. Here we go again. Let's grab the input. Something tells me we might even want to play around with the example as well. So let's grab the example. There we go. So we basically have to run Game of Life until we reach a fixed point and then count the number of occupied seats. Okay. There's only one thing that's really different from Game of Life, and that's that in Game of Life, when you reach the edge, it's like an infinite universe. It keeps growing, but here we have a fixed map, or a map of fixed size, I mean. So the problem is actually a bit easier. Okay. Again, we have like a two-dimensional grid of 3 distinct states. Like we have floor, which doesn't really matter. We have a empty seat and we have occupied seat. I'm thinking, do we need the empty floor? I don't think we really need the empty floor. Maybe in part 2 we start moving chairs. Maybe. Yeah, let's keep the empty floor in our data structure as well. But I like to represent. Let's quickly start. Let's not start with the big input. Let's start with the example. So it's a list of strings, yes. Let's start parsing it. What's the data structure we're going to use? Just a two-dimensional list. Two-dimensional list, or like a hash map mapping coordinates to whatever's at that location. That also works. I feel like using maps. Maps betrayed me yesterday, so it's time for their redemption. Let's first define a union type. What are we gonna call it? A position is either floor, empty, or occupied. What's the best name for this? Don't know. If I don't know, I just type state. Empty. No, floor, or an empty seat, or an occupied seat. And our parser then is why am I writing a list comprehension? Let's quickly, because when I work with two-dimensional grids, I always get mixed up with like the X and the Y axis and the point of origin. So let's make that clear from the start. Eric, or the examples in Advent of Code always use like 0, 0, and then grow, or their X coordinate goes here. So this is X, and their Y coordinate goes here, and that's actually very easy to work with. So this would be X increasing, this would be Y increasing, and this is both. Writing with a mouse, it's not easy. So this is Y. So a new line in our input means increasing the Y coordinates. Let's index. Yeah, sure. Let's index our lines, and then for every line, actually we can use a for comprehension. That'll be clear. So for every line, and then for every column in line, let's also index that. Yep. And let's just return line was Y. I'm just gonna pull out the, yeah, let's call it row. I'm just gonna pull out the X and Y coordinates directly. And what we return is a coordinate, and we parse the whatever it is in that column. That should give us a list of all the cell or all the places in the grid with their contents. Let's try it out a bit. So let's look at the small example again. We start with an empty seed. And there's a row entirely made of seeds, okay. We start with an empty seed, yeah, and there should be a row entirely made of seeds. It's too hard to say. So, empty seed, floor, empty seed, floor. Empty seed, floor, empty seed, floor. Yeah, okay. This is what we call a steekproef in Dutch. Good enough. But instead of working with the raw characters, let's parse the characters into our union types. Yeah, let's write a quick parsing function. If we meet a dot, this is floor. If we meet a uppercase L, this is an empty seed. I'm going to call the state empty seed because empty and floor, it'll confuse me. And if we meet a bound symbol, it's an occupied seed, but that doesn't exist in our input just yet. Okay, let's quickly write a problem function. There we go. And that's a list, but instead of a list, let's make it a map. So that's a list, yeah, let's make it a map, because every coordinate can have only one state. So this is a map.offsec, and this transforms a list of like pairs, like coordinate and floor is a pair. It converts this to a map or a lookup table. So now we have a lookup table mapping coordinates to their states. Okay. Do we use the terminology of maps? Layout, let's call it layout. So now we can represent the map or the layout. Now we need our next step I want to do is write a function that applies the rules to a given instance in time. So layout is the world in an instance in time, and now let's write a function that takes a layout like this and applies the rules to it, and it gives us like the new state of the world. Yeah, let's do that. It's not the first time we've did this. Like previous years of Advent of Code, we also had game of life kind of puzzles. Yeah, I'm gonna call it tick because my brain has been warped by doing game of life puzzles for years now. But tick means like apply all the rules to this world or to this layout at the same time. So we get a layout and it returns a new layout. If you look at the exercise, it's like saying all the rules have to be applied simultaneously. So this means whenever we like handled a rule in the upper left, this does not have impact on what we do in the next cell, because they have the rules or the cells like evolve simultaneously, not one after the other. This is actually a really good match for immutable data structures and stuff like that, because you can't accidentally alter the world and take new stuff into account. So these are the 3 rules, or actually there's 2 rules, like an empty seed becomes occupied, and occupied seat becomes empty if it's too crowded, and otherwise just keep going. But if you look at these rules, there's like no occupied seats, 4 or more seats are also occupied. So we need to find the surrounding seats, or we need to be able to navigate our map and look at our neighbors. So let's quickly write a neighbor function. Given a layout and a coordinate. Yep. And we need like all 8 surrounding seats or surrounding positions. So we need to do something with coordinate. Yep. What do we need? So if we end up somewhere here, for example, let's do it this way. If we end up here, we need to like go 1 up, 1 down, right, left, and to the diagonals. So basically we need to generate 8 coordinates. Yeah, we need to generate 8 coordinates, like go on to the left, go on to the right, going up, going down, and do the diagonals. So let's generate 8 coordinates. And coordinates are, I'm just gonna plop all the deltas in a list. So going to the up left diagonal is like decreasing both coordinates by 1. Going up is decreasing the y coordinate by 1. So x stays the same, there's 0 delta, and y is up by 1. And then this should be 1, 1, or 1 minus 1. So this is like, look at the row above me. What's to the left of me? X decreases by 1. X decreases by 1. I say it and I mistype it. That's crazy. And then here would be our current position, and this would be X increases by 1. Yes. And we're a row down. So we're to the left, so X is decreased, and we're a row down, so Y is increased. This is the same X position, but there we go, and this is 1, 1. I think this is it. I think these are our deltas, and I try to the layout is a bit like a, hopefully it makes sense. So these are our deltas, and then we just map every delta. We do something for every delta. We offset the coordinate with are given a, let's also extract these. So it's a pair of an x and a y coordinate, and this is just current coordinate x offset with the x coordinate of the delta, and current coordinate y offset with the y. So these are all our coordinates we need to look at. And now let's just look at them all up in the map. So layout map dot try, yeah, because we can be at the edge of the maze. It's not maze, we can be at the edge of the map, and then when we try to look to the east or to the right, there's nothing there. So I'm gonna do a try, which returns an option, and this takes a key. In our case it's a coordinate, so it's literally a coordinate. And again, we need to map over the coordinate. So we try to find this coordinate in the map, and if there's nothing there, we can ignore it. So try to find it and only keep the relevant ones. I think that was called sec.pick. Takes a function. takes a function that returns an option and returns... No, it's not pick, it's choose. Takes something that... Is this correct? What's the return type of neighbors? It's a sequence of A. Yeah, it doesn't matter. We haven't typed. Let's try it out on the example. So if we look for the neighbors of 0, 0 in our layout, it's the other way around. It gives us 3 neighbors, which makes sense because we're at the corner. It should give us this location, and this location. So 2 empty seats and a floor at 0, 1. Yeah. 2 empty seats and a floor at 0, 1. We throw away the location information, but I think that's not a problem. Yeah, we don't need it. So now we can like find what's happening around us, and that's enough to start implementing the rules. So let's go back to our tick and take a sip of coffee because programming Conway's Game of Life for the 35th time gets tiring. Okay, let's go. So we need to do something for every space in the layout. Doing something is always the same, just mapping. It's a map, not a sequence, but I think a sequence is a map. No, it's not. Is it? If I do this, will things crash? I think things will crash. Let's try to tick on our initial layout. Yeah. What am I even doing? There we go. So do something with it. Does this work? Yes, but it generates a sequence of key value pairs. It forgets the fact that it's a map. I mean, that's not too bad. But let's make it explicit, map dot to sequence. So now it's really explicit what's happening. We take a map and we return a sequence. We don't really need to return a sequence. I'm getting sidetracked. What do we need to do? We need to apply a rule for every space in our current layout. So let's do a map and let's apply the rules given our entire map. So let apply rules given a map and a current location. And location is a combination of a coordinate and the state there, but state is actually irrelevant. Yes, and location is, so it's a key value pair. Let's explicitly convert this because otherwise we're gonna get confused. Map to sequence. So now we have a list of key value pairs. Or yeah, a list of pairs containing the coordinate and the state. So this is a single coordinate and a state. We don't touch the coordinate, but we will be changing the state. This is all lining up, all the types are lining up, yes. So for the current coordinate, we look up the neighbors. And what are the rules again? Oh yeah, we do need the current state, sorry. If the current seat is empty and there are no occupied seats, so actually we need to count the number of occupied seats. So the occupied seats are the neighbors and only the occupied. So let's rip out the occupied. Everything else we don't need. And let's count them. Count by. Could we have used count by? I don't know. What's wrong? What does neighbors return? So we go over our layout and we find it's a state. Yeah, we even printed it out. Where is it? Where is our neighbors? It was like just 3 states, so I don't see what's wrong here. It's saying the type pair of a function type of a pair to a sequence. Oh yeah, we need to provide the layout to our neighbors function. If I type my function signatures, this would not happen. Cool. Still going strong. So these are the number of occupied neighbors, and now we can do something. Let's pattern match. So next state is what do we need to base a rule on the current state, so that's S here, and on the number of occupied seats. Okay. So if a seat is empty, so seat is empty seat, and the occupied seats, there's 0 occupied seats, then the seat becomes occupied. And what's the state called? It's called occupied. Cool. What's the other rule? If a seat is already occupied, so if it is already occupied and the number of occupied seats is 4 or more, when we have 4 or more occupied seats, then we become empty. In all other cases, we don't care about how many occupied seats there are, we just stay the same. So this is the next state, coordinate remains the same, and instead of the original state, we have the next state. I think we're there. So now if we look at this apply rules, this applies the rules for a given location, given the entire map. And tick just takes every location and applies the rule to it. So this returns a list of key value pairs representing the new status. And let's just throw that back into a lookup table. I think this is enough to implement a tick. Can we tick? We can tick. So after the first tick, everything is occupied. That's not correct. Let's print it out in its entirety. I was not expecting everything to be occupied. Oh no, not everything is occupied. So every empty seat has become occupied, but there's still some floors. For example, 0,6 is a floor. 0,6 is like the 6th here. 0, 1, 2, 3, 4, 5, 6. Yeah, that could be correct. So this is a single tick, but we need to keep ticking until nothing changes. Also known as find the fixed point of the tick function. Fixed point is literally apply a function, look at what you had before as input and look at the output. If these are the same, then stop doing it, and otherwise do it again. So let's write a function to do this for us. So we get a function, and input, for example. And let's calculate the next state by applying the function to our input. And if our next state is completely similar to the input, then we're done. Otherwise, keep going. So this needs to be recursive. So keep going, applying the same function, but not on the initial input, but on the next input. So this is a quick fixed point implementation. And let's run fixed point on our tick function and give it the layout. So this keeps running until we have no more changes. And hopefully this works without going into an infinite loop. It does. So I think we might be done. Empty seats and occupied. So there's an empty seat in 0, 2. 0, 2 is the y coordinate was what again? Yeah, going down. 0, 2 is an empty seat. That is correct. 0, 0 is occupied. Okay. Steekproef genoeg. So this looks correct. Let's do it for our input now. No. What do we need? How many seats end up occupied? Again, we are already filtering. This is the how many are occupied. Trick we're applying. What? Oh yeah, we don't need the coordinates anymore. So let's just throw them away. Now let's only keep the occupieds and count them. There we go. So the example gives us 37. That is correct. Our entire input gives us hopefully something else. Oh no. Oh no. Calculating our fixed point is taking a bit longer for the real input. Probably my choice of data structure wasn't the best. Okay, it's good enough for part 1, so good enough for part 1. So let's just keep going. Yeah, 1 gold star, closer. Oh, I hope my code is performant enough for part 2. I don't want to rework it. Okay, let's look at part 2. Oh no, we made a mistake in our modeling process. They don't care about adjacent seats, they care about the first seat they can see. The first seat they can see. Okay, instead of considering just the 8 immediately adjacent seats, consider the first seat in each of these 8 directions. Interesting. Okay, so we're looking at our 8 neighbors. The definition for neighbors is now changing a bit. It's not of a distance of just 1, it's like as far as possible until we hit a seat. Empty seat below, so this is the seat, which see 8 occupied seats. So if we go up, we hit this seat. If we go down, we hit this seat. Yep. If we go diagonally, probably we'll see that seat. That's an interesting variation. In this case, the leftmost empty seat would only see 1 empty seat, but cannot see any of the occupied ones. The empty seat here would see... What? The empty seat here would see no occupied seats. Oh yeah, no on top, no to the left or the right. Diagonals will just fall through, yeah. It now takes 5 or more visible occupied seats. Okay, so the rules also change a bit, but not that much. I think, given these very concrete examples, that's a good starting point for part 2. Yeah, that's a good starting point to change our find neighbors implementation. How will we do this? How will we do this? Instead of a delta, we need to basically calculate a vector and keep going until we hit an empty seat or unoccupied seat or fall out of the layout. Yeah, interesting. So first thing we're going to be tweaking for part 2 is this baby right here. Thinking, actually, this approach still is somewhat the same. So these are the 8 directions or the 8 vectors we need to move in, but instead of trying just once, we need to keep trying until we hit nothing or a seat. Yeah, so every empty, what's it called? Every floor we meet, we can ignore and we just can keep trying harder. Okay, let's test drive this a bit. So let's take this, looks like one of the easier examples. Just gonna jumble in my tests in between my code for now. So this is the input. Let's format it a bit so it makes sense. Come on. There we go. What's wrong? Okay. This is a simple example, and we try to find the neighbors. Given example 1 parsed x1, there we go, and we need to look at location 0, 1, 1, so 1, 1. So this is the seat that only finds the empty seat to the right. Yeah, and currently in the current implementation, it looks around and it only finds empty floors. That is correct. Okay, so these are the 8 deltas or the 8 vectors. That remains the same. What needs to change? Instead of this, and then doing this, so coordinates, yeah, actually these 2 steps need to apply it. We need to apply these steps iteratively. Let's call this find first seat in layout given a direction, and it returns an option. Yeah, it returns an option if we find something, it returns none if we find nothing. And then we can keep the same kind of structure. So for example, coordinates, no, we just need the deltas, so let's do deltas and only keep the ones that return something when we call find first seat in given the layout and our current. Oh yeah, we don't only need the direction, we also need the current location. So find first seat in CX, CY. Actually, let's call this location. We don't need to open it up right here. So for every delta, try to find the first seat in the given direction. So arguments mixing up. layout, location, and then the delta, the direction. And this can go. This can go, yeah. And this is something that kind of belongs here, but differently. Should we just write a recursive function? Yeah, why not? Let's try to look it up by applying the direction once. So let's open them up. So this is X and Y not yield, come on Visual Studio, and this is delta X and delta Y. So let's try to look up the offset. Let's call this next. So this is X plus delta X, Y plus delta Y. So this is the same thing as we're doing here. Let's then try to look it up. And if we find nothing, then we're done. This is an option.map, but okay. If we find nothing, then we're done. If we find an occupied seat, no, if we find some, but it's floor, special case, then we find the first seat in layout in the next, but in the same general direction. And otherwise, this is what we need. So what's happening? We find the first seed given a layout and a current location and a direction. We calculate like the next step in that direction. We try to look in that place. If we find nothing because we fall off the map, we're done and we can conclude there's nothing here for you. If we find something, but the something is like an empty floor, we take a next step in that direction. Or if we find something other than floor, like an empty seat or an occupied seat, we're done. And that's the first seat we encounter. So I think this might be our first seat finding algorithm. So I'm expecting this to now return the one seat to the right, the one empty seat to the right. Yes. And let's do it the same for 2 x coordinates further. So that should be a occupied seat to the right and an empty seat to the left. Yes. Okay, this is important enough to maybe pull into a test. So let's test this. There we go. Yeah, it should only be the empty seat, that's correct. And if we try to do it for 3-1, we should have an empty seat and an occupied seat. Yes, that's correct. Cool. This is recorded for eternity now. Yeah. Let's pull the examples out of our test runs to see my logs more clearly. Okay, so this is the new neighbor algorithm, which is way more intensive than the first one. So I'm thinking that performance-wise, we might have a problem. There was a second variation of the problem. Huh? Yeah, people seem to be more tolerant. It now takes 5 or more visible occupied seats to become empty. 5 or more. Where's our 4 or more? It's here. So now it's 5 or more. Other rules still apply. Empty seats that see no occupied seats become occupied. Yep. Seats don't change and floor never changes. Yes. This is the new algorithm, and we should end up with 26 occupied seats for the example. So let's parse the example again with the new rules. There we go, with the new rules. Fixed point was quick for the small example, and we end up with 26, which is correct. But now, let's do this for the real deal. How long are we willing to give it before we give up and try to optimize this? Let's say I'm going to slowly drink some of my coffee. Even slower. Yeah, no. It's taking... Oh, there we go. We won't be winning any speed contests today, but I don't care. And it's correct. So that was Advent of Code day 11. Let's quickly look at what happened. I represented the states as a union type for the 3 different cases, because then it's easier to exhaustively pattern match, but actually we're never exhaustively pattern matching, so that's maybe not that relevant. But I like working with like a finite set of different states rather than just characters everywhere. It constrains your state space. Then I made a probably stupid decision to work with a lookup table or a map instead of a 2-dimensional array, because I think that might have been faster, because we're always converting from the map to a list and then back to a map. So this is where the performance issue is lying, probably. For part 2, we had to like tweak the neighbors thing to don't look at the one further, but go in the general direction until we find something. We implemented this using recursion and options. Now I'm thinking, do we have a better way? Nah, it worked. And the rules changed a little bit. And what I found cool today was that implementing the rules, it's pretty clear if you use pattern matching. It's like, okay, these are my neighbors. These are the number of occupied neighbors. What's my current state? What are the occupied neighbors? And you can just list every case here. It's pretty declarative. And this is how we handle to apply all the rules at the same time. Like we take a layout and we apply rules for every position in that layout, but using the same layout as input, so they all happen at the same time. And next cool part was we need to do something until there were no changes in the map, and we did this by finding the fixed point of the tick function. Yeah, that's it. I hope you enjoyed today's Advent of Code in F#, and I will see you tomorrow. Bye.